How's it going? This is Mr. Murray coming to you with a little do now video for Course 2 Honors. And I want to take a moment to welcome you all back to week 10 of the closure. Hopefully, I'm not the first teacher to do this. So, today we're going to jump back into probability. And this is actually going to be the day where we're going to wrap up independent events, dependent events, and the multiplication rule. And actually, this brings us to more or less a close with probability. And so I thought I would wrap up by doing a little do now regarding probability and card games. And for this activity, it is going to help you to know what the multiplication rule is. So if you haven't seen my probability video about independent and dependent events and the multiplication rule, I do suggest that you watch that because it will help you understand how you would even start by solving this problem in terms of stuff we've learned about in the unit, because you can do it, but the multiplication rule is essential. So you finally made it to the Encore Casino. You mastered probability and think you can use it to your advantage. So you start with Blackjack. The values of each card are shown in the diagram below, and I'll move down to that in just a second. Here are some basic rules of Blackjack, and there are many rules, and I understand that, so here are just some basic ones. You start by being dealt 2 cards. If you're dealt an ace and a jack, then you have Blackjack and you automatically win. Okay? Otherwise, you can hit, which means you can be dealt more cards until you stand, meaning you are done. Now, when you're done, the dealer deals to themselves, and they're required to hit until the sum of the values of their cards is 17 or higher. If at any time the sum of the values of all of the cards that have been dealt to you or the dealer is more than 21, then you or the dealer would bust. So if you got, for example, let's say you were dealt a 3 and a 9, and you were at 12. Now you get dealt a jack, and you're at 22. You're over 21, and that means you lose. If the same thing happens to the dealer, they win. Keeping in mind, if you think about it, the higher than your number so far, for example, if you think about this board right here, if I'm currently at 18, the probability that I'm going to get a card that pushes me over 22 is a lot higher than if I was at 7. Because if you think about it, how many cards could put me over 22? Well, a king, a queen, a jack, a 10, a 9, an 8, a 7, a 6, a 5, a 4. And then you've got 1, 2, 3, 4 different suits. So you have a really, really high chance of going bust and losing all your money depending on what your current sum is. And that has to do with probability. So here's what I want to know. These 4 questions. 1, what is the probability that you get a blackjack? That means, what is the probability that you are first dealt an ace and then dealt a jack? Now, I know that sometimes there's requirements about what the suits have to be, but for this, I'm allowing the ace to be anything, any of the 4 aces, and the jack to be any of the 4 jacks. Okay? The order, whether it's an ace or a jack, does not matter. That is to say, an ace and a jack or a jack and an ace would give you blackjack. Okay, what's the probability of being dealt 2 of the same card? So by that I mean a 5 and a 5, a 9 and a 9, a king and a king, whatever, and another one of a different suit. Okay, what's the probability of being dealt 2 face cards? So that is to say, of being dealt 2 cards that are jacks, queens, or kings. And finally, what's the probability you're dealt 2 cards with values less than 10? Okay, because that could potentially be good or bad depending on what the actual sum is. Okay, so these are the 4 questions we need to figure out. For the purposes of these questions, assume the following. First, every card has an equal chance of being drawn. Okay, that's important. 2, there is no replacement of any cards at all. So cards are never replaced. They're drawn and that's it. And then just remember, whenever you're being dealt cards, you're always using the numbers underneath them in these pictures to figure out their value. Okay, and in general, order does not matter. If you're dealt the Jack of hearts and the Jack of spades, it's the same outcome as if you're dealt the Jack of spades and the Jack of hearts for the purposes of being dealt two face cards. Okay, so please pause the video. Under those parameters, find these four probabilities. Then when you're ready, unpause and you can see what I got. All right, so let's jump right in and let's try these probabilities. So basically, this problem essentially hinges on, remember, the multiplication rule. And the multiplication rule says that the probability that two events, A and B, will both happen is equal to the probability that the first event happens times the probability that the second event happens, given that the first event has already happened. And this can go on forever, right? We could have A and B and C, and it would be the probability of A times the probability of B, given that A has happened, times the probability of C, given that A and B have both happened, etc. Now, if you're in a situation where you have independent events, then the probability of B given A is the same as the probability of B. So you may have also seen it as the probability of A times the probability of B if they're independent events. In general, this is how the multiplication rule works, though. Okay, and we need to use this version in particular because we're being told that the cards are not being replaced. Now, we know from this game to this game to this game to this game, we're resetting at 52 cards every time. And if you didn't make that assumption, you may want to go back and check your work, as well as the assumption that it's only me playing. I don't care about the dealer's cards. I'm going to assume that first I get dealt one card, then I get dealt another card. Okay, so some things to think about. So for the probability of getting a blackjack, so to get a blackjack, I first need to be dealt an ace or a jack, and then whichever card I didn't get, ace or jack, the first, so I either have to get an ace or a jack and then an ace, right? Ace, jack, jack, ace. Now, it doesn't matter for the purposes of this problem what the suits are. I know it's got the term blackjack in it, and sometimes people say something's got, one of the cards has to be a black card or something. I don't know. I'm not an expert with blackjack. So for the purposes of this problem, I'm just going to assume one of the cards is an ace, the other of the cards is a jack. So what's the probability of a blackjack? So if we think about it, in the beginning, there were 52 cards that we could have been dealt. And if we're assuming that this is truly shuffled such that we have an equal chance of getting every single card in the deck, then there are 8 cards that we can initially get. Because the first card could have either been an ace or it could have been a jack. Okay, so there's 8 possible cards that I could have been dealt. Now, given that I was just dealt one of those cards, there are now only 51 cards in the deck. To figure out what the other number has to be, well, let's think about it. And I'll just change this to number 1 so the multiplication signs don't get confused. If I was dealt an ace, then I would have to get one of the 4 jacks, right? So here's how I would think about it. Imagine you're sitting at this table and you want to win and you want this outcome to occur. How many cards, when they first deal that first card, are you going to say, yes, I still have a shot? And how many are you going to say, oh, game over, no way, right? So where the 8 comes from is, if you think about it, there's 8 cards, 5, 6, 7, 8, where if you see them, you know you still have a shot of getting a blackjack. If you get any card like a 2, a 5, a king, no matter what suit, it's game over. There's no way you're getting a blackjack because you have to have an ace and then a jack. So if you see an ace or a jack, you know you're good. But here's the thing. If you see an ace, let's say I see an ace, I can't see another ace, right? Because if I see another ace, then I don't have an ace and a jack. Similarly, if I see a jack, I don't want to see another jack, because if I see another jack, then I've got 2 of the same card, right? I don't have a blackjack. So based on given that I've been given one of these 2 cards, either an ace or a jack, there are only 4 other cards remaining that could be the card I want. That is to say, either I've been given an ace and then a jack, or a jack and then an ace. Now, if you break, so what you end up getting is 32 over 52 times 51. Now, the other way to break this down is using the theoretical probability that we've already figured out from the previous lesson. And now theoretical probability is harder to do than the multiplication rule, but it will still yield you the same results. So this is the multiplication rule. If we use theoretical probability, well, basically, how many different ways can you, so if you draw 52 cards, you don't replace them, you draw 51 cards, right? Because think about it. For each card, there are 51 other cards that could be paired with it. So there's 52 cards, each of which has 51 other cards that can be paired. So there are 52 times 51 possible combinations for 2 cards. How many of them are either an ace jack or a jack ace? So I have this ace with 4 jacks, this ace with 4 jacks, this ace with 4 jacks, and this ace with the 4 jacks. Or I could have the jack with 4 aces, because the order does matter. Because the fact that a card has already been dealt changes the probability that the second card will be dealt. So the second card probability depends on the first one. So the order does, in theory, to a certain extent matter. Though if you get an ace jack and a jack ace, it would be interpreted the same way. Okay, so notice the jack with 4, the jack with 4. So notice how many 4s are there. There are 8 4s. So you can see either way, if you use theoretical probability by counting the combinations, along with a little bit of conditional to remember that a card's already been dealt, you get 8 times 4, which is 32 out of 52 over 51. If you use the multiplication rule, you get the same thing. But notice how much less time it takes to do the multiplication rule. So that's my argument there. Okay, if I go ahead and simplify this, what I'm going to do is I'm going to take a step back to this part of the problem, because 4 goes into 52 13 times. So what I actually end up getting, I'm going to actually come over under the cards. I'm going to write my answer right here. See, I'm already making a box for it. So this cancels and becomes 1. 52 divided by 4 is 13. Okay, so then I don't think there's anything else I can do. So 13 times 51 is 663. So the top multiplies across and gets me 8. The bottom multiplies across and gives 663. So that's a percentage of about 1.2. So you have a 1.2% chance, okay, of getting a blackjack. Now, here's the thing that you might not know. In reality, a casino actually combines a number of decks together. So what they might do is they'll say, all right, let's open up 5 decks. Take all the decks, shuffle all 5 decks randomly together, and then put them there. So the issue is, though, one, you don't know how many decks there are. So you don't know how to figure out the sample space. So it doesn't, and then because you don't know how many total cards there is, you can't figure out the event either. And it matters, right? Because the more cards you throw into the deck, the less of a chance you have of getting an individual card that you're looking for. So that's something worth considering. So the probability might actually be even lower than this. But if you think about it, right, that's the idea. If you're the casino, we want to lure the customer in thinking that, wow, look at this, you're going to get this big payoff. But in reality, you have only about a 1 in 100 chance of actually getting that. Now, right, that it's tempting enough and you see it happen where you might want to have this thing happen to you. But in reality, you're likely to end up losing a lot of money. So dealt 2 of the same card. I want the probability of getting doubles. Now, sometimes in blackjack, there's a rule called doubling down. And what that lets you do is if you get 2 of the same card, you can split your hand into 2, and then you can place a bet on each hand, play 2 hands at the same time, and then end up potentially winning even more money. So I want to know, what's the probability I'm going to even be able to do that? So first, in the beginning, it doesn't really matter what card I get. I could get any card that I want in the whole wide world, right? Because it's just two of the same card, right? And remember, by same card, what we mean is two of the same like type, but different suits. So like a jack of spades and a jack of hearts, a six of spades and a six of diamonds. So in the beginning, I've got 52, not over 51. I've got 52 out of 52 possibilities. I can get whatever card I want. It doesn't matter, right? Because if I'm dealing doubles, imagine you're sitting there at the table, you're dealt card. The first card, it doesn't matter what you get. You're still in the game to get doubles. Okay, now that a card has been dealt, there are only 51 cards left in the deck. Okay, given that there's 51 cards left in the deck, well, think about it. Choose any card. Think about the card that imagine you're getting dealt in your head. Now, if that card had been dealt to you, let's say it was the five of hearts, how many more of that type of card would be in the deck? There would only be 1, 2, 3 other types of cards of the same like face. So like if you'd been dealt the four of clubs, there would be the four of spades, the four of hearts, and the four of diamonds, right? And that's true for any other card you can think of. So it's 52 over 52 times 3, the remaining out of the remaining cards in the deck. I'm going to cross out 52 over 52 because we know it's equal to 1. And when you multiply a number by 1, the answer stays the same. So 52 over 52 has no effect on the final answer. So I'm going to cross it out to indicate that. It's almost like if things added up to 0, you'd cross them out to say, look, this stuff doesn't matter anymore. It's canceled out. So my only thing I have to worry about is 3 over 51. And now 51, the 5 and the 1 add up to 6. So I know that 51 is divisible by 3. And it is actually 17. So you have a 1 out of 17 chance of being given doubles. Okay, so 1 out of 17 chance is about a 5.9% chance, meaning you're almost 5 times more likely to get doubles, in a sense, than to get dealt a blackjack. So you have more of a probability of being dealt two of the same, like a pair, than being dealt a blackjack. Now, what's the probability you're dealt two face cards? All right, again, assuming a reset, so that we're now back to 52 cards in the deck, right? These are like 4 scenarios playing out in our head. Okay, so again, we think about it. How many cards, if we saw them, would we say we're still in the game? So there are 3, 6, 9, 12 face cards. The jack, the queen, and the king times 4 suits. Assuming that one of them is dealt, there would only be 51 cards left, and there would only be 11 face cards left because one of the 12 face cards had already been dealt to you. So what that means is that this will cancel, and that will become 3 because that's divisible by 12, and by 4, and we already know that 52 over 4 is equal to 13. Okay, now I'm going to cancel out the 3 because I know that 3 goes into 51. We already know 3 and 51, that's going to be 7. So I believe what I end up with is 11 over 13 times 17. I'm going to double check that. So let's see if I do 12 times 11. I get 132. Okay. Yep. All right. So I do confirm I get the same thing. I just did some work on my calculator showing the decimals were the same. So it's 11 over 21, over 221, which is approximately equal to 4.9%. So you're actually more likely in our kind of naive circumstances here to be given doubles or a pair than to be given 2 face cards. Okay, interesting. So, okay, a couple other things to notice. Just keep in mind, we could have used theoretical probability. How many different ways could you get face cards? So you could have a jack with any of the 3 jacks. So the jack, any jack could go with 3 other jacks, 4 of the queens, or 2 of the kings. So it's 4, 5, 6, 7, 8, 9. Right? Any of the 3 jacks. Sorry, the 4 queens or the not 2 kings, 4 kings. So notice 4, 8, 11. See where the 11 comes from? And then, keeping in mind, the queen, the king. So the queen could then go with the 3 queens, the 4 jacks, or the 4 kings. And then the king could go with the 3 kings, the 4 jacks, or the 4 queens. So notice there's 11 in each times 3, but then there are 4 suits. You don't know you're going to get the jack of clubs off the bat. You could have also gotten, right, the jack of spades, the jack of diamonds, or the jack of hearts. So then it's 11 times 3, because there are 3 cards, times 4 suits, but 4 times 3 is 12, right? So you can see that's where the 11 times 12 comes from, and then over the 52 times 51 possibilities. So you can do it with theoretical probability or the multiplication rule. Again, I'm going to advance the argument that the multiplication rule is a little bit easier in this circumstance. All right, last one, dealt 2 cards with values that are less than 10. Can't be equal to, but are less than 10. For the purposes of this, we're going to assume that the ace is allowable because the ace is considered to be 1, possibly. If you didn't factor that into your math, I would consider doing that. So how many cards are values less than 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. By the way, why do I care? Well, the reason that I care is because if I get two cards with values less than 10, then that means their numbers are going to add up to a value less than 20, which means that, that situation where I'm in the middle ground, right? If they added up to a small number, I might consider playing it out. If they added up to a number that was like, 20, well, they can't add up to 20 or more. So I might have to hit. So this is the situation where I'm in kind of like, I don't know. If I'm in a face card, I'm stopping right away because I'm at 20, right? This is a little bit more dangerous. So anyway, there's 9 cards per suit. There's 4 suits. So that means that there are 36 cards I could possibly get that are good, where I know I'm still in the game, and there are 52 cards total in the deck. Okay, now I know that once I've been dealt one, there are only 51 cards that remain in the deck. Out of those 51 cards, there are only 35 remaining cards whose values are less than 10 because one has already been dealt out. Now, we can simplify because 36 and 52 are both divisible by 4. And that's basically, let's see. So I get 140 out of, 140 out of 13 times 51, which is 663. Okay. All right. Now I got to do some other checking here. I'm sorry. So if I divide by 4, this is what's going on. I noticed that number was a little small. So actually, this needs to actually not be 4, but it needs to be 9. Because you're dividing by 4. So it's 9 times 35. And 9 times 35. And actually, since that's a 9, maybe I can clean this up a little bit more. So maybe I'll divide this by 3 and this by 3. Because I figure if I divide 51 by 3, that'll make my life a little easier. All right, so let's take 2 on this one. This is a tough one. So 3 times 35 is 105. All right, and now 13 times 17 is 221. And 105 over 221, so we should be just shy of 50%, and I get about 47.5%. So we have about almost a 50-50 chance of being dealt 2 cards less than 10. So hopefully you're able to get this one right. Congratulations if so. The first one is 8 over 663, or 1.2%. The first is 1 over 17, or 5.9%. The third is 11 over 21, or 4.9%. And the last is 105 over 221, or 47.5%. Now, you may have gotten some different fractions depending on your simplification. Just please keep in mind with regard to the fractions that you should always simplify your final answer. All right. So that's why I always simplify at this point, because it's easier to simplify here, I feel, than to simplify here. But you do it wherever you want, as long as the final answer is think about including a simplified fraction and a percent. Again, just make sure you look out for what we're asking you to put your final answer. And so are we asking for a fraction, a decimal, a percent, or a combination of those? All right, folks. But in any case, thank you very much for watching, folks. Best of luck. And remember, you can do it. All right, thanks for watching. Have a wonderful day, and don't forget to love